the depth buffer. In this video we're going to talk about a very important thing called the frame buffer. So the frame buffer in computer graphics is a collection of image buffers for rendering a frame. When you output color values from the fragment shader, then these end up in the frame buffer. More specifically in the color buffer that is inside the frame buffer. So in the frame buffer we have the color buffer, but we also have a depth buffer. And there's also something called a stencil buffer. We're going to talk about the stencil buffer later on in the course, but for now let's focus on the color buffer and the depth buffer. So the color buffer is just where the color values outputted from your fragment shader are written to. But the fragment shader also writes to the depth buffer. So it writes to the depth buffer the depth values, the transformed z coordinates. And these say to the GPU which of the fragments are further and which are closer. The depth values in this image are like this, that the larger values, the lighter gray values, are further away from the camera, and the darker values are closer. More specifically, they become 0 at the near plane and 1 at the far plane. And the GPU uses this depth buffer in order to know which objects or which fragments are in front of other ones. This is called depth testing. So let's say we have rendered this ground on the color buffer. And of course the depth values of the ground are in the depth buffer as well. So this is what we have already rendered. Now we're rendering a new object. We're rendering this hut on top of this ground. And the fragment shader is currently rendering some pixel, let's say over here. It has calculated its color and it has calculated its depth. Now what it does next is it compares its depth value, the one from the fragment it's currently rendering, to the depth value that is already in the depth buffer at the same coordinate. This is to understand if the newly drawn color, the newly drawn fragment, should be in front of what is already in the color buffer or behind. And if it's supposed to be behind, then it's not going to draw it because it's behind another object, thus you wouldn't see it. But if it's in the front, if this depth value from this hut pixel is in front of the pixel from the ground, so this one is in front, then it's gonna overwrite the color in the color buffer at that location. So in this particular instance, the depths are compared. Yes, this yellow that's from the hut should be in front of this green that's from the ground because the depth values are corresponding like that. And thus we overwrite this green with this yellow. Now in modern GPUs there is also something called the early depth test. So actually this depth comparison is done before the fragment shader calculates this color, so that it wouldn't have to waste resources in calculating this color only for it to be discarded because the depth test fails. Another thing to say about this depth testing is that you could disable it if you want, or you could configure it in some other way. Later we will talk about the stencil buffer, and then the result of the depth test can influence what values will be written to the stencil buffer. But in the standard pipeline, the depth testing is very useful because the GPU does not know which objects are in front of what other objects, and maybe even some objects are like intersecting with each other. So it's really about fragments, so which fragments are in front of other fragments. Even in this hut, there is a surface of this hut that is inside this hut, so it's kind of self-occluding. So the GPU needs to somehow know which of these pixels need to be in front of other pixels. There is also something called set fighting, and this refers back to the way we calculate the depth. Remember, the depth had this hyperbolic curve, and we had more granularity in the depth near the near plane than we had near the far plane. So let's see this case. We have these points A and B, and they're pretty far away from each other. One is at z minus 400 and another is at z minus 450, 50 units apart. Let's calculate the z values, or let's say the depth values of both of these points after they've been projected. So these equations are directly from the perspective projection matrix, and this is the homogeneous point division. Once we have calculated these equations, we have set the near plane to 1 and far plane to 500, so we can just substitute these values in there. we will get these results. Well, they're pretty long, but you can also see that they're quite close by. So the projected depth of A is 0.9989, and for B it's 0.999. Now in the GPU, these depth values are actually converted to integer values, and those have a limit on how many different integer values the memory can hold. So for this particular example, let's say that our max int is 256. So this is the largest integer we can hold. Now if we multiply the depth values we found here with 256, and then, well, we have to floor them because we want to store them as integers, we can see that both of those result in the same 255 value. So from the GPU's perspective, if the max int is 256, it only has 8 bits to store values in, then from the GPU's perspective, those 2 points are at the same distance from the camera. So it doesn't know which one should be drawn on top of each other, which one should be discarded, and this can cause some flickering in the render. For example, like this. So over here, what I've done is I've put 2 planes on top of each other, so at different coordinates at different times, the GPU doesn't know which one of these planes should be in front of another, and thus it's really flickering. Well, this is kind of a contrived example, but also in different video games, especially older ones like Skyrim, you might see flickering in the very distant geometry. So if you climb the highest mountain in Skyrim and look as far as you can, you might see like the water or some mountains in the distance are kind of flickering, and if you move the camera, sometimes one face is in the front and sometimes another face is in the front. And this is called this set fighting. Now the depth buffer also has different applications. For example, in one of the practice sessions, you have this task where you need to make these soft particles. And this is exactly done with the depth buffer. For example, if you sample the depth buffer, you can see if there is some scene geometry that's already drawn that's close by to whatever fragment you're currently drawing. This is how these soft particles work. So when you're drawing these transparent particles, you can check that is there already a similar depth value than what would be the depth value for the current fragment at this coordinate. And if there is, you know that this fragment is already near some scene geometry that has been drawn. So you can increase its transparency and then make it like fade out when it gets closer to the scene geometry, and thus avoiding these alias lines or these lines here. Another example is shadow mapping, which we'll talk about later on in the course, but there we use additional cameras to render only the depth buffer. So we use this depth buffer to calculate which areas should be in the shadows and which should not be, and we're only rendering the depth buffer with these additional cameras, ignoring the color buffer entirely for them. And on the right you see that this is the result of one of those cameras. It only sees the depth of these objects moving around in the scene. Now from this video you should understand the frame buffer, which includes the color, depth and stencil buffers. Some of these can be disabled, so not all of them have to exist in the frame buffer together, but these are the buffers that it holds. You also know about the depth buffer, that it stores the transformed set coordinate, the depth, and by default the depth buffer is hyperbolic. So there's more granularity near the near plane and there's less granularity near the far plane. You also now know about the depth test. So this depth test checks the depth buffer and sees which colors should overwrite the values in the color buffer. And you also know about set fighting, which happens when the GPU cannot decide which fragment should be in front of another fragment. And this often happens near the far plane, where the objects far away get very close depth values.